So in this lecture, I'm just going to do problems from the homeworks on infinite series. I'll start in section 9.2. So problem number 1, we have an infinite series that starts like this. And we're asked to compute the first 5 partial sums. So S1 is just the first number. S2 is the sum of the first 2 numbers. S3 is the sum I'm doing some problems on infinite series. So,
okay.
I'm going to do a few problems from each of these sections that we've covered so far in the lectures. So in section 9.2, we're given an infinite series that starts like this. You might recognize this is the sum of the reciprocals of the squares. So the S1 is just the first term in the series. S2 is the sum of the first 2 terms. S3 is the sum of the first 3 terms. So that's 5 fourths plus a ninth. So that's something over 36. Looks like 49 over 36 and so on. Do you have any questions about any of the homework problems?
No, not right now.
Okay, I'm just going to go through and just pick some that sort of sample everything that's being covered.
Okay, I'll just take a look into it.
In problem number 9, it says verify that the infinite series diverges. So in problem number 9, this is n equals 0 to infinity, 7/6 to the nth power. So the nth term in this series is 7 over 6 to the n, which is bigger than 1 for all n. And there's a theorem that says that if the infinite series summation a sub n converges, then the limit as n goes to infinity of the nth term is 0. And in this series, the nth term doesn't go to 0. In fact, it's always bigger than 1. So that's the reason why this series must diverge. Number 25 is the series summation n goes from 0 to infinity, 5/6 to the n. But this is a geometric series. And if you have a geometric series, summation ar to the n minus 1, n goes from 1 to infinity. The limit is a over 1 minus r if the absolute value of r is less than 1. And here, let me write this in this form just to make it look weird. This is the sum 5/6 times 5/6 to the n minus 1. So as n goes from 1 to infinity. Right, so this is just 5/6 to the n. Actually, the better way to write a geometric series is if you have summation r to the n goes from 0 to infinity. If the absolute value of r is less than 1, this is 1 over 1 minus r. So here, the ratio is 5/6. This is 1 over 1 minus 5/6. So that's equal to 6. So the sum of this infinite series is equal to 6.
Okay, that one's pretty easy using the formula.
Yeah. Well, the geometric progression is the most important infinite series. That's the one that's used by far the most everywhere in calculus and everywhere in mathematics. Let me look at some other ones that look interesting. 57 and 67. Let's look at 57. So number 57 is an infinite repeating decimal. And we're told to write this as a geometric series and as a fraction. So this is 0.0, and the part that's repeating is 7.5. So this is 0.07575757575, and so on forever. So what does this mean? If you write this out, this is 0 over 10, 7 over 10 squared, 5 over 10 cubed, 7 over 10 to the 4th, 5 over 10 to the 5th, 7 over 10 to the 6th, 5 over 10 to the 7th, and so forth. Or I could write this 7 over 10 squared is 70 over 10 cubed. So this is 75 over 10 cubed. And this is 75 over 10 to the 5th. And this is 75 over 10 to the 7th. And the next term would be 75 over 10 to the 9th, and so on forever. So if you look at this carefully, this should look like a geometric progression. Suppose I factor out 75 over 10 cubed, and then I get 1 plus 1 over 10 squared plus 1 over 10 to the 4th plus 1 over 10 to the 6th, and so forth. This is 75 over 1,000 times 1. This is 1 over 100. This is 1 over 100 squared. This is 1 over 100 cubed. Let's see, what is 75 over 1,000? If I divide 25 into that, I get 3 over 40. And this is the infinite series summation 1 over 100 to the n, as n goes from 0 to infinity. And this is a geometric progression. This is 3 over 40, 1 over 1 minus 1 over 100, which is 3 over 40, 100 over 99. So 3 into this goes 33 times, and 40 into this is 2 and 5. So this is 5 over 66. So if I did my arithmetic correctly, this infinitesimal is equal to the fraction 5 over 66.
So the 75, that's from the last two digits from the problem.
Well, so the problem is we're given the infinite repeating decimal 0.0 and then 75 repeating. So
Yeah.
0.75, 75, 75, 75, and so on forever. And when you write this, when you just translate what decimal notation means, each digit is that digit over a power of 10. This is 0 over 10, 7 over 10 squared, 5 over 10 cubed, and so forth. And I just pair off these numbers. So each of these is 75 over 10 cubed, 75 over 10 to the fifth. So you have to do a little bit of arithmetic.
Yeah. Okay.
Let me do a couple of problems that use the integral test in section 9.3. So the integral test says if you have a positive continuous function f of x, always positive continuous for x greater than or equal to 1, and we let an be the value of the function at n, then the improper integral converges if and only if the infinite series converges. So let's look at some of the problems. Let's see, in section 9.3, 1, 3, 5, 7. Let's look at number 5. So problem 5 is summation n goes from 1 to infinity, e to the minus n. And if we let f of x be the function e to the minus x, then f of n is e to the minus n. So this series converges if and only if the integral from 1 to infinity of f of x converges, which is the integral from 1 to infinity e to the minus x dx, which is the limit of the integral from 1 to b of e to the minus x dx as b goes to infinity. This integral is minus e to the minus x evaluated from 1 to b. So this is the limit as b goes to infinity, minus e to the minus b, minus e to the minus 1, which is plus e to the minus 1. And as b goes to infinity, this goes to 0, so this is e inverse. So the improper integral converges, so the series converges. The series does converge. Let's look at number 31. Number 31 is summation 1 over n cubed, n goes from 1 to infinity. So this is summation n goes from 1 to infinity of f of n, where I pick f of x to be 1 over x cubed. So the value of the function to n is 1 over n cubed. We have to look at the improper integral from 1 to infinity of 1 over x cubed. So that is limit as b goes to infinity of the integral from 1 to b, x to the minus 3 dx. The limit b goes to infinity. The integral of x to the minus 3 is minus 1/2 x to the minus 2, 1 over 2x squared, evaluated from 1 to b. So this is the limit, b goes to infinity, of minus 1 over 2b squared, minus is plus 1/2. And as b goes to infinity, this goes to 0. So this is 1/2. So this improper integral exists. Therefore, the infinite series converges. That makes sense?
Yeah.
Number 57 is more interesting. It says, find the positive values of p such that the infinite series n goes from 2 to infinity, 1 over n log n raised to the power of p, converges. And we start with 2 because when n is 1, log 1 is 0, so I can't divide by 0. So we want to compare this to the integral of the function 1 over x log x to the p dx. Let's say we go from 2 to infinity. For what values? So if this integral exists, this series converges. So in this integral, we want to, this is going to be the limit as b goes to infinity, the integral from 2 to b, 1 over x log x to the p dx. What is the integral from 2 to b of 1 over x log x to the p? So if we substitute u equals log x, so du is 1 over x dx, this becomes the integral of du over u to the p, where u goes from log 2 to log b. What is this? U to the minus p. This is 1 over so u to the 1 minus p, 1 over 1 minus p, evaluated from log 2 to log b. So this is 1 over 1 minus p log b to the 1 minus p minus log 2 to the 1 minus p. So we want to know what happens as b goes to infinity. Well, if p is equal to 1, so if this exponent is positive, this goes to infinity. This goes to infinity if p is bigger than 1. And if p is less than or equal to 1, if p is equal to 1, this converges. So this is, but it converges if p is less than or equal to 1. So the answer is find the positive values of p such that this series converges. The answer is 0 less than p less than or equal to 1. So you have to work out the integral, and you get the result.
Wait, I'm sorry. After you substitute, what did you do in the n where it says 1 over 1 minus p, and then it's the log of b?
So The integral we need to examine is the integral from 2 to infinity of 1 over x log x to the p dx.
Yeah.
And to do that, we integrate from 2 to b, 1 over x log x to the p dx. And if we make the substitution, u equals log x, so du dx is 1 over x, so du is 1 over x dx. When we substitute, we get the integral of du over u to the p.
Yeah.
And so this is, so u to the minus p, this is 1 over 1 minus p, u to the 1 minus p. We're just integrating u to the minus p. And we're evaluating this when x is 2, log, u is log 2. And when x is b, u is log b. So we're evaluating this from log 2 to log b. So actually, I want to say, so let's look at the first, this is the case p different from 1. Because if p equals 1, I can't divide by that. This is p different from 1 and positive. So you get 1 over 1 minus p log b to the power 1 minus p minus log 2 to the power 1 minus p.
Oh, okay. Okay.
And now what happens is b goes to infinity. So there are two cases. If p is less than 1, this is positive. So this goes to infinity if p is less than 1. And if p is greater than 1, this is negative.
Yeah.
You have 1 over something getting bigger and bigger, and the limit is, the limit exists. Right, so if p is bigger than 1, the limit is just 1 over 1 minus p minus log 2 to the 1 minus p. It doesn't matter what it is, but it exists. So this converges if p is bigger than 1, diverges if p is less than 1. And what about the case p equals 1? Then I have the integral from 2 to infinity, 1 over x log x dx. Again, I make my substitution. U equals log x. So du is dx over x. This becomes the integral of just du over u, which is log u, from log 2 to log b. And this also goes to infinity as b goes to infinity. So in fact, I did it backwards when I did it the first time. This diverges if p is less than or equal to 1. So this integral converges for p bigger than 1. That's what I should have said. So
Okay.
you just have to do the improper integral carefully.
Yeah.
Let me do a couple of problems in section 9.4. So this uses the comparison test. So suppose we have series where an is less than or equal to bn, and these are positive for all n, and we want to compare the two infinite series summation an and summation bn. So the comparison test says what is almost sort of obvious if you think about it a little bit, namely, if the series of bn's converges and the bn's are bigger than the an's, then the an's convert the series. Because this is going to be bigger than this, but this goes to something less than infinity, so this has to. So summation bn converges. If the big one converges, then certainly the small one converges. On the other hand, if the small one diverges, then the bigger series definitely has to diverge, because these are series of positive terms. So that very simple statement is the comparison test. So let's look at some of the problems. 7, 9, 11. Okay. So number 7 is to determine the convergence of the series summation n goes from 0 to infinity, 1 over 4 to the n plus 1. So we want to invent a series to compare this to. So in this series, this is like my series summation an, where an is 1 over 4 to the n plus 1. A slightly bigger number is just 1 over 4 to the n. I'll call that bn. And what can we say about summation bn, which is summation 1 over 4 to the n? Well, this is a geometric progression. This converges, in fact, to 1 over 1 minus a fourth, which is the third, which is 4/3. So summation bn converges implies summation an converges. So the problem was to consider this series and determine whether or not it converges. To find what it might converge to is much, much, much harder, often impossible. But just to determine convergence, we have to invent out of our imaginations a series to converge that compare it to, whose convergence or divergence is easy to figure out. Let's look at number 9. Summation log n over n plus 1. Now, if I look at the term log n over n plus 1, that's going to be bigger, at least for n greater than or equal to 3. This is bigger than 1 over n plus 1. In fact, if we want something that's true for all n, I could just make this a half times 1 over n plus 1. It doesn't really matter. So this is my an. Nope, sorry. This is going to be my bn, and this is going to be my an. So these are positive terms, and summation 1 over summation bn, summation an, n goes from 2 to infinity, is summation n goes from 2 to infinity, 1/2, I can take that out, 1 over n plus 1, or a half summation 1 over n, and goes from 3 to infinity. But this series diverges. So using the integral test in the book, it worked out the harmonic series, that is the series of reciprocals of all the positive integers, this diverges. And this, it's just the same thing except for dropping a couple of terms. This diverges, so the smaller series diverges, so the bigger series, which is this one, diverges. Let's look at number 17. So the fact that the harmonic series diverges is used often in comparison tests, because you can often compare things to this series. So number 21, let's see, 21, comparison series, 17, yeah, let's look at 17, number 17. Number 17 is summation n goes from 0 to infinity, 1 over the square root of n squared plus 1. So you look at that and you say, well, 1 over this n squared plus 1 is almost the same as n squared. The square root of n squared plus 1 will be almost the same as the square root of n squared, which is n. So this term is very much like 1 over n. And the series of 1 over n diverges. So a reasonable thing might be to try to compare 1 over n and 1 over the square root of n squared plus 1. And unfortunately, this isn't smaller than this. See, if it were smaller, then this diverges, therefore this would diverges. But we could make this, let's say, 1 over 2n. Let's see, is this true? Let's do an experiment. So this is true if this is the same as square root of n squared plus 1 less than or equal to 2n. If you square both sides, n squared plus 1 less than or equal to 4n squared, 3n squared greater than or equal to 1, that's always true. So this inequality is okay. And if I let this be an and this be bn, the summation an is 1/2 summation 1 over n. And this diverges. So the smaller series diverges, so the bigger series diverges. So this is a new kind of mathematics. It's not like in calculus 1 and beginning of calculus 2, we're just doing derivatives and integrals. There's some integrals that are involved in the integral test, but we're not differentiating or integrating anymore. We're doing something completely new. And it takes a little bit of practice to get used to it. Let me do one more and then I'll quit. This is number 23. So we have the infinite series, n goes from 1 to infinity, 1 over n times the square root of n squared plus 1. And if you look at this, this is almost like square root of n squared plus 1 is approximately n. So a natural thing would be to maybe want to compare this to 1 over n squared. And in fact, 1 over n times the square root of n squared plus 1. If I make the denominator smaller, I get a bigger fraction, 1 over n times the square root of n squared, which is just 1 over n squared. So if I let an be this and bn be this, what about this series, summation 1 over n squared? We know summation 1 over n squared converges. I mean, in general, the p series we know that summation 1 over n to the p converges if p is bigger than 1. And here the exponent is 2, which is definitely bigger than 1. So therefore, summation 1 over n square root of n squared plus 1 converges. Okay. So it's kind of an art form to learn how to determine convergence and divergence of infinite series. It's a very nice kind of mathematics. Anyway.
Yeah, it's just the formulas. It's not really that hard. It just depends on the problem.
Of course.
Yeah.
Yeah, I mean, there are easy problems and there are hard problems, but it's also a matter of just doing enough problems that you learn the techniques.
Yeah.
And, so these are very hard to do the first time usually, but the more you do, the better you get at it and the easier the problems look.
Okay.
That's all for this morning.
All right.
All right.
Thank you.